Hello everyone, welcome to Source classes. This is Tushar Shaw, and in this video we will be continuing to solve the UPSC CS main 2020 paper that we were solving since the last 6 videos, I guess 6 or 7 videos. This one is probably the 7th video. Okay, so in this video obviously we'll be starting from question number we have question number 3 up to, we did up till question number 3D. So we will be starting from question number 3E in this case, and obviously as I have told you earlier in the like in this format of video that we have been lastly we had solved quite a lot of number of multiple choice questions, but this paper is specifically subjective type, so you have to write each and every answer as I am writing them for you. Okay, each and every step is important. That is how you will be getting full marks for each and every answer. Okay, so let us, without any wasting time, let us look in the questions that are given to us, and we will be completing it quite easily. Okay, so question number 3E, it says that write down the Debye-Hückel limiting equation for ith type of ionic species in the salt solution with symbolic significances and units. Okay, so we have to write the DHLL, Debye-Hückel limiting law for ith number of species. Okay, ith number, ith type of species. Okay, here we don't have to write the derivation or anything. We are provided 10 marks for writing this question answer correct. So what we need to write is write down the equation and explain each of the terms with their units, and thus we'll be getting full marks for this question. Like it kind of an easy question. All you need to know is know the equation. Memorize, like you need to have the equation memorized, and the terms in the equation you just need to understand them. Okay, so let me just write down the equation for you, the Debye-Hückel limiting law, that is with the pointer. Yeah, so the equation is log of gamma I is equal to minus a z1 square zi square I to the power half, where I is equal to half of summation zi square. Okay, zi square. Okay, I'm sorry, not Ci square. Okay, Ci. Now this is the overall equation. Now let me explain the terms for you. Okay, so here a, the value of a is a constant obviously. Okay, a is a constant. Its value is 0.509. Z is the charge on each species, like the charge on ith species, charge on ith species. Here we are taking the square every time we are writing z, so the negative or positive doesn't matter. The only magnitude would be considered. Okay, I is known as the mean ionic activity coefficient. Okay, mean ionic activity coefficient. Now I also has a formula which we need to find out before putting the value of I in this formula, that is I is equal to half of summation of Ci square. Here Ci is the concentration of ith species, okay, of ith species, and Zi is the, obviously, as I have already mentioned, charge on the ith species. Okay, so this is the case. Yeah, so these are all yeah, so the let us the all the terms are now explained. Now let us look at the units. Okay, so the unit of a is, the unit of a here is mole to the power half, kg to the power half. But we are taking the concentration term, the Ci, that is the concentration term, to be in molality. Okay, molality. So the unit of C would be unit of C would be moles per kg. Okay, as the unit of molarity is taken. Z is unitless because it is just the charge of the species. Okay, yeah. So this is the case. Now when, let us write down some conditions. So when log gamma j, or we may say I, is equal to, is less than 0, uh, a ai is equal to uh, into ln j, mi, sorry, not mi. Okay, where I, a is the activity of the ith species. Okay, activity of the ith species. So if we just draw the graph for this, what kind of graph we'll be getting is, um, so let us draw the graph quite correctly. So we have I to the power half in this axis, that is the x axis, and we have log of gamma I in this axis. So the graph that we'll be getting is kind of like this. Okay, all in the negative side because of the equation that we have written already in the above equation, that is we have started the equation being negative. Okay, this part is already negative, so the graph would be in the negative side. Okay, so this is how you will be writing the question, and you have to like write 1 or 2 lines explaining all the phenomenon that is occurring. Okay, so yeah, so this was the question number 3e. So let us move on to question number 4a. Okay, so question 4a is kind of an like big question. You have to write a lot in this question, and obviously 10 marks is just given, so that is a injustice, you may say. So what is LCAO? So you have to write down the firstly the full form. That is the linear combination of of atomic orbitals. This is the full form of LCAO. So when you will be writing the definition down, you will be writing the full form first. Okay. So question says, what is LCAO? What are the bonding, non-bonding, and anti-bonding orbitals? Okay. So illustrate with the suitable diagram with the help of an H2 molecule with the framework of molecular orbital theory. Okay, so we have to like firstly explain what is linear combination of atomic orbitals all about, and then we have to explain the structure of like one example, that is the molecular orbital diagram of H2 molecule. Okay, so let us now look into that. Yeah, so firstly psi mo. So writing quantum mechanically, we will be seeing that psi mo is equal to ci psi 1 ci psi I c1 psi 1 plus minus c2 psi 2. Okay, this is the integrated rate law, not the rate law, the integrated form of the Schrodinger wave equation. Okay, the integrated form of Schrodinger wave equation. Okay, so obviously from this equation we can draw two plots. Okay, those two plots would be the exact framework about how the molecular orbital theory is formed, like how we can draw the from the atomic orbitals, how can we convert that into molecular orbitals. Okay, so let me just draw the diagrams for you. um, so the first diagram is this one. We have chi square over here, and we have the R value. All these are explained in quantum mechanics. So if like when I'll be teaching you the classes related to the quantum mechanics, the topic wise, so then I'll be explaining how these are occurring. So for this question only, we are just trying to explain the question answer. So we'll be just drawing conclusions from the direct explanation. Okay. Okay, so let me just draw the graphs for you. We have firstly this kind of plot would be obtained, and then this kind of plot would be obtained, both of them for the species A and B. Okay, this point is for A and this point is for B. Now and overall these A and B species would be combining to give a molecular orbital. Okay, so the molecular orbital would be kind of like this. Okay, so this one is chi square A, I'm sorry, this one is psi a square, this one is psi b square, and therefore this one is the psi square bmo. Okay, What is a BMO? I'm just explaining. Let me just firstly write down the graphs, then I'll be explaining. Okay. So again we'll taking chi square and the R value. We'll be having these kinds of plots for the individual species, that is the atomic orbitals. For this side we have A, for this side we have B. So in this case we'll be having another plot. So let me just draw the plot for you. Now this drawing is obviously not up to the scale. I'm drawing using my pen tablet and I don't have much experience writing this. So like the drawing is kind of bent. You may just use your pen and draw it quite perfectly. Okay. So obviously these two initially these two are the psi a square and the psi b square, and this part is the psi square ABMO. Okay, this point is the chi square ABMO and this point is the chi square BMO. Now what is BMO and ABMO? So from the diagrams you can see that the atomic orbitals of A, the species A and B, had their wave function size probability densities as psi a square and psi b square in the both the cases. Now these two in one case, case one, in first case they combine to give this kind of graph, which we call it as a BMO, which has a higher energy, and in another case we call it we see that the plot is kind of lowered from the psi a and the psi b square values to give the psi square ABMO, which is the anti-bonding molecular orbitals. These would be having lower energy. Why? The explanation would be um, so in this case we have the BMOs would be normally having electrons and therefore would be at higher energy state, and the ABMOs would be at lower energy state from the electronic perspective, because they won't be having any electrons as such in normal cases. Okay. Now energetically, or when I'll be drawing the H2 molecule, you will see that the ABMO always rise in energy, stays in up from the BMO. Compared to the BMO, the ABMO always stays in a higher energy position. Okay. So this was all about the explanation for LCAO, how molecular orbitals are formed from the atomic orbitals. Now let us look at the example that we need to discuss. Okay. The example is about the H2 molecule. Okay. So for a H2 molecule, let me just draw the atomic molecular orbital diagram for you. Okay. I am not drawing any such plots or individual plots of psi. I am just drawing the total plot obtained from the energy, like from the free energy diagram. Okay. This axis we have energy or potential energy, you may say, and this axis has R, that is the radius on the nucleus, obviously. This part is from the atomic orbital of 1s of one hydrogen, and this one is also is a 1s of another hydrogen. Okay. These two 1s orbitals have, each of them have one electron in it. We denote electrons by arrows. Okay. Single electron means one upward facing arrow, and pair of electron means uh, this kind of simultaneous upward and downward arrow. Okay. Half of the, like the face would be, the one side of the face would be reduced to half. Okay. So this would be forming two parts. Firstly, so this would be the molecular orbital, okay, of H2, of H2 here. These two electrons would descend, obviously, to gain stability, as they are in lesser energy, to form a pair of electron. Okay. And this orbital would be staying empty. This orbital is known as the BMO, obviously, as I have explained, lower in energy. This part is known as the ABMO, which is higher in energy and above from the 1s species, like the original atomic orbitals. Okay. Now the explanation for BMO and ABMO are already done in the I've already explained. The one explanation that is required, which the question asks, that is NBMO, that is non-bonding molecular orbital, which is this line. Okay. This line connecting the 1s orbitals and the line between the BMO and the ABMO, this line is known as the NBMO. Sorry, NBMO, which is the NBMO here is the non-bonding molecular orbital. The name convention here, like from where the name is coming, it is not asking the question. You just had to explain in case of the molecular orbital diagram, what is the significance or what is the use of NBMO. So it is there present in the in between the ABMO. It has energy level in between the BMO orbital and the ABMO orbital. Okay, and normally it connects the atomic orbitals of the two species in case of a diatomic molecule like H2. Okay, diatomic. Okay, so this was all about the explanation for this question. Okay, so let us wrap this video up. In the we did up till question number 4a, so we'll be moving on to question number 4b in the next video, and then we'll be completing it. Okay, so thank you guys for this video. I'll see you guys in the next one.